Dielectric properties of materials. Here is the classification of dielectrics. So dielectric materials can be classified into three classes: simple dielectrics, paraelectrics and ferroelectrics. And here is the effect of electric field on each of these classes. In simple dielectrics, under the influence of electric field, in simple dielectrics, dipoles are created. Means one part of the molecule become partial negative and other parts of the molecule become partial positive. And its creation of dipole takes place in the presence of external electric field. In the paraelectric materials, the permanent dipoles are already present, and under the influence of electric field, these dipoles orient themselves in certain alignment. And ferroelectric materials they also contain the dipoles. They are polar. Spontaneous polarization takes place in ferroelectric material, and under the influence of electric field, orient domains of aligned permanent dipoles. We will study in the later slides about this. Ferroelectricity. The group of dielectric materials called ferroelectric, which was the third class of dielectric material. These ferroelectric materials, they have spontaneous polarization. Means they have permanent dipoles, and their dipoles are aligned spontaneously in the absence of an electric field. In a sense, ferroelectrics are the electric analog of the ferromagnetic. Means this is analog with the ferromagnetic materials. In the ferromagnetic material, there is permanent magnetic behavior. In ferroelectric, the polarization can be changed and even reversed by an external field. When we apply external electric field, the polarization can be changed and even polarization can be reversed. In ferroelectric material, this type of spontaneous polarization, the permanent dipoles are present, which are spontaneously aligned. By application of external electric field, these polarization can be changed, and even this polarization can be reversed. Mean negative poles go in this direction and positive poles go in this direction. In most ferroelectric crystal, the non-polarized structure becomes stable. If the crystal is heated above critical temperature, the ferroelectric Curie temperature. This ferroelectric Curie temperature is that temperature. Below this temperature, the material would be spontaneously polarized, and above this temperature, the material would be non-polarized. The material below this Curie temperature Tc, the material polarized. This phase is called ferroelectric phase. And above this Curie temperature, the material is non-polarized. Mean this is not now ferroelectric. Mean ferroelectricity exists below this Curie temperature. So non-ferroelectric material, where the material is not polarized, not spontaneously polarized, this non-polarized phase is called paraelectric phase. The change of spontaneous polarization at temperature, Curie temperature, can be continuous or discontinuous. Mean it can take place in continuous or discontinuous manner. The Curie temperature of different types of ferroelectric crystal range from a few degrees absolute to a few hundred degrees absolute. Each type of ferroelectric material have different range of Curie temperature. From practical standpoint, ferroelectrics can be divided into two classes. The first class. In the first class, The spontaneous polarization. The spontaneous polarization will take place only on one crystal axis. An example of this is Rochelle salt, potassium hydrogen phosphate. This is the formula of Rochelle salt: potassium hydrogen phosphate, ammonium sulfate, guanidine aluminum sulfate, hexahydrate. Another example of this first class of ferroelectric material, glycine sulfate, columenite, and thiourea. Other examples. And in the second class, the spontaneous polarization occurs in several axes, mean along x-axis, along y-axis, along z-axis. Spontaneous polarization can take place. An example of barium titanium oxide. This is a perovskite type structure, ferroelectrics. This cadmium nobelium oxide, and other examples are of second class of ferroelectric materials. Here is another classification of ferroelectric material. Uh, what are two types according to this classification? Proper ferroelectric materials and improper ferroelectric materials. Proper and improper. In proper ferroelectric materials, for example, barium titanium oxide, potassium hydrogen phosphate, Rochelle salt, these are all examples of what? Proper ferroelectric material. The spontaneous polarization is the order parameter. Mean the spontaneous polarization takes place, and in improper ferroelectrics, the spontaneous polarization can be considered a byproduct of another structural phase transition. Mean by changing the temperature, phase transition takes place, and it is another type of phase transition, and as a byproduct, spontaneous polarization is created. Here the spontaneous polarization is created as a main product, and here spontaneous polarization is created as a byproduct, and these are called improper ferroelectrics. Actually, in ferroelectric crystal, there are certain regions of homogeneous domains. This crystal is divided into certain regions. This is a ferroelectric crystal, and here these small portions are called domains. So first we see what are domains. In this small region, for example, this is one of the small region. This is one domain. The dipole moments of individual molecules are in one direction. Mean polarization is in one direction, and the overall of all molecule is shown by this arrow. So in this one part, all the molecules have polarization which is aligned like this. So overall is represented by this vector. So these small portions where the polarization of individual molecules is aligned, these small portions are called domains. In ferroelectric material, in ferroelectric crystal, ferroelectric, according to the domains, ferroelectric materials are classified into two classes. So first class consists of domain with parallel and anti-parallel polarization. Means one domain is parallel, other domain is anti-parallel, like this diagram A. Whereas ferroelectric of second class, this B is of ferroelectric of second class. That can assume much more complicated domain configuration, because here it is going upward, it is going from left to right, some is coming from right to different. It means it is more complicated as compared to the above one. The region between two adjacent domains are called domain walls. Means the boundary which is between the two adjacent domain, that is called the domain wall. The spontaneous polarization changes within this wall. The spontaneous polarization changes its direction. Means the electric field can change the direction. The material which is spontaneously polarized within this boundary between this wall, this spontaneous polarization, the direction of the overall polarization depend on this spontaneous polarization. Okay, when we apply external magnetic field on this or this ferroelectric material, what will happen? The electric field means one positive plate and the other negative plate. These all domains will be aligned. The polarization of all domains will be aligned because the negative pole of all molecule will be towards positive plate and the positive pole of all molecule would be towards negatively charged plate. So external magnetic field will change the direction of these domains.
So again the same diagram.
Electrorestriction. Electrorestriction is the mechanical deformation, mean change in the shape, deformation in dielectric material. And this is what is the reason of this mechanical deformation of the dielectric material? Due to polarization in the dielectric material. Sometime by the application of external electric field, the polarization take place, and due to this polarization, mechanical deformation will take place. How due to polarization mechanical deformation will take place? When electric field is applied, this electric field cause polarization, mean it induce dipole moment. Due to polarization, charges are displaced from their equilibrium positions. And due to this displacement of charges, the overall dimensions of the solids are changed, which is called mechanical deformation. And it is actually the term used for this mechanical deformation is electrorestriction. So by the application of external magnetic field, electrorestriction takes place. But once the electrorestriction has taken place, it cannot be reversed. It cannot be reversed. However, mechanical stress applied to neutral medium cannot induce dipole moment. Electrorestriction has no inverse. Mean by applying the stress, neutral material cannot induce dipole moment. Means opposite of this electrorestriction cannot take place. If a mechanical distortion creates a voltage, the effect must be caused by permanent dipole moment anchored in the structure without a center of symmetry. Sometime due to this mechanical distortion or due to this electrorestriction, a voltage can be created, and this creation of voltage is due to the presence of permanent dipole moments which are created in the structure without center of symmetry. Piezoelectricity or pressure electricity. Electricity or electric polarity resulting from the application of mechanical pressure on a dielectric crystal is called piezoelectricity or pressure electricity. When we apply, for example, this is a dielectric material, when we apply the pressure, mechanical pressure on this dielectric material, what will happen? Electricity will be produced or electric polarity would be produced, and this electricity which is produced is called piezoelectricity or pressure electricity because this is produced by applying pressure on the dielectric material. The application of a mechanical stress means we are applying pressure. We can also say we are applying stress. So this stress produces a certain electrically non-conducting crystals and electric polarization which is proportional to this stress. Means in some dielectric crystal this stress produces electricity, and amount of this electricity produced is directly proportional to the applied pressure. If the crystal is isolated, this polarization manifests itself as a voltage across the crystal, and if the crystal is short-circuited A flow of charges can be observed during loading. Means in a single crystal, the electricity will be produced due to this polarization and voltage will be produced across the crystal, and if the crystal short circuited, a flow of charge will be observed during loading.
Application of voltage between certain phases of crystal produces a mechanical distortion of the material. When we self-apply a voltage between certain phases of crystalline structure, due to this external voltage application, what will happen? Mechanical distortion of the material will take place. Crystalline structure will be distorted. It is opposite to that we have previously studied in the slide, that when mechanical stress is applied, a voltage is produced. This is when external voltage is given to the crystal. Mechanical distortion takes place in the crystal. This reciprocal relationship is referred to as piezoelectric effect. The phenomenon of generation of voltage under mechanical stress is referred to as direct piezoelectric effect, and mechanical strain produced in the crystal under electric stress is called converse piezoelectric effect. So this is converse piezoelectric effect. Piezoelectric effect are two types: direct piezoelectric effect and converse piezoelectric. Direct piezoelectric effect is that when we apply mechanical stress on the material, this is the material, and we apply what? Mechanical stress. A voltage is produced in the material, and this is called direct piezoelectric stress. And when here is a material or crystal, and we apply voltage, external voltage, and here in the crystal, what will happen? Distortion of the material. This distortion of material is called converse piezoelectric effect. So these are opposite to each other. Here the stress is applied, here the external voltage is applied. The piezoelectric effect is demonstrated in the figure. This is the figure showing the piezoelectric effect. A dipole within a piezoelectric material. B, a voltage is generated when a material is subjected to compressive stress. These are piezoelectric material, and in the piezoelectric material, these are dipoles, positively charged plate, negatively charged plate, and this is a dielectric material. When on this dielectric material, mechanical stress sigma is applied in both directions, and due to this mechanical stress, a voltage is produced, a current flow is produced across, and this type of material, which by application of stress produce electric current, are called piezoelectric material, and this effect is called piezoelectric effect. This is what is direct piezoelectric effect. Piezoelectricity occurs only in insulating materials. It does not take place in electric conductors. Only few ceramic materials exhibit this property. Piezoelectric materials are used as a transducer. Transducer means they convert one form of energy into another form of energy. Here, this type of transducer convert mechanical strain, which is applied on piezoelectric material, into electrical signal or voltage. And here is the application of this conversion, mechanical strain into electrical signal, which is used in transducer. Transducers are used in microphones. In microphone, when we speak in the microphone, mechanical strain is produced by vibration of our sound, and transducer convert this into electrical signals when we speak in the microphone. And phonograph pickups are the same thing. That it is phonograph. Phonograph is the early form of gramophone, which is used for production of sounds, and this also works on the same principle. Mechanical strain is converted into electrical signal. Vibration sensing elements, such elements which sense the vibrations, and vibration produces mechanical strain, and mechanical strain is converted into electrical signals. And the converse effect, the opposite effect, in which is for reverse piezoelectricity. Mechanical output is derived from an electrical signal. We applied external electric field, and mechanical distortion takes place, and it is used in such devices as sonic and ultrasonic transducers. Means this transducer that convert the sound energy into electrical energy. Sorry, they convert electrical energy into sound energy. Like headphones, they convert electrical energy into sound energy, loudspeaker, and cutting. I think it is mistakenly written here. Here, the application of piezoelectric material is in which devices piezoelectric materials are used. Frequency resonators, gramophone pickups. We have previously studied the sound in the sound energy is converted into electrical energy. Filters, ultrasonic flow detectors, underwater sonar transducer, air transducer, uh, phones, microphone, hearing aids. In all these things, the piezoelectric materials are used. Uses of dielectric, piezoelectric, and electro-optical devices in dielectrics are used in such type of devices in capacitor, resistors, and strain gauges, thermionic valves, radiation detectors, electric devices, dielectric amplifier. Dielectrics are usually used as ordinary insulator in power cables, signal cables, electric motors, and dielectrics are used in transformers and various forms of switchgear and generators where the dissipation problem of heat is active. Heat flow in the different parts, in between the different parts, dielectric materials are inserted or filled, due to which there is no electrical contact between the different parts of the generators, and then there is less production of heat. Dissipation problem of heat is active, and due to this dielectric material filling, there will be less problem of heating. And a common way of getting rid of it is to insulate with a transformer oil. Oil is a dielectric material. Mineral oil is used.